Hello, everyone. Welcome to our webcast today. Mission Impossible. Analyze over 300 TLS sessions in 1 hour. My name is Yvonne Wheaton. I'll be your moderator today. I represent Software Diversified Services. So our agenda today, like I said, I'm going to be doing the introductions and I'm going to tell you a little bit about Software Diversified Services, but really the heart of this is going to be Nalini Elkins, the CEO and founder of Inside Products, will present to you how they accomplished Mission Impossible, the analyzing of over 300 TLS sessions in 1 hour. Nalini is a recognized leader in the field of computer performance measurement and analysis. She's an experienced software product designer, developer, and planner. She's also been a founder or co-founder of 2 startups in the high-tech arena. So lots of experience here. Nalini has a strong computer network background, but specializes in network performance analysis, measurement, monitoring, tuning, and troubleshooting of large enterprise computer networks, including TCP/IP and SNA. In 2014, Nalini was awarded the prestigious A.A. Michelson's Award by the Computer Measurement Group, CMG. She was recognized for her contribution to the industry, innovative software analysis tools, and contributor to the IPv6 standards. In 2017, Nalini joined the advisory board of the Indian Internet Engineering Society. Since she will be presenting to you the Mission Impossible analysis over 300 TLS sessions in 1 hour. Quite interesting. Okay, so a little bit about Software Diversified Services. Software Diversified Services, a global leader in mainframe software, has been named to the Cybersecurity 500 list of the world's hottest, most innovative cybersecurity companies for second quarter of 2017. SDS was founded in 1982 and supports over 25 products for security, encryption, data compression, and network monitoring. SDS has over 35-year history of delivering award-winning support and customer-centric IT infrastructure solutions. We have licensed over 1,000 enterprise clients worldwide, offering customers quality mainframe software, documentation, and award-winning tech support that combine for unsurpassed value. SDS is an IBM partner in development and an advanced member of the IBM Partner World. We're pleased to be presenting today's webcast with our product partner, Inside Products, whom we have a suite offering in the IP Problem Finder arena, which consists of 4 products: TCP Problem Finder, SSL Problem Finder, which we'll talk about today, IPv6 Problem Finder, and DNS Problem Finder. You can find out more about these products at www.sdsusa.com. As I mentioned, Nalini Elkins from Inside Products will be covering the SSL Problem Finder today in our webcast, Mission Impossible, analyze over 300 TLS sessions in 1 hour. So I'll now hand the presentation over to Nalini. Nalini?
Hi, this is Nalini Elkins, and today we're going to talk about analyzing over 300 TLS connections in an hour. I know that sounds like, how could I ever do that? But I'm going to lead you up to that, and by the end of it, I think you're going to believe me. So let's back up a little bit, and let's talk about why we are doing secure sockets or TLS, all of that kind of stuff anyway. So here's a little story. It's a very sad story. It's about an ATM in Kiev in Russia, which started sending out cash at random times of the day. And nobody had touched it. And cameras showed that all of a sudden people came by just at the right moment. What a coincidence. And swept up that money. And what had happened is that there was a group of hackers that had stolen money from banks throughout the world. What they do is to send a malware or phishing program, and so they can get into the bank's administrative computer. And the malware records keystrokes, etc., and they also allow the hackers to control the computers remotely, like using remote desktop, that kind of things. And so using all this kind of stuff, they've learned to steal money very, very nicely in very profitable ways to themselves. They transfer money into their own accounts. And of course, the most interesting one that we just talked about, which is to direct ATMs to dispense money at set times. And so then, of course, they just happen to be there and pick up that money. So one of the things that we're doing, this is kind of an escalating war between the hackers and the security folks, between the black hats and the white hats, if you will. So what people are doing throughout the world is using a protocol called transport layer security. You may know that as Secure Sockets Layer. That was the original name, Secure Sockets Layer, or SSL, and it is still very widely used today. The real name, as far as the protocol suite at IETF is concerned, is TLS, or Transport Layer Security. It is the most widely used security protocol in the world. It was first developed by Netscape, and it has some major functions. Authentication of the server. That means, are you really who I think you are? Are you really the bank that I'm trying to connect to? Data privacy and integrity. Whenever you hear privacy or data privacy, what you're going to think is encryption. And so this data will be encrypted, so you cannot see it over the wire. And integrity, of course, that it has not been modified in flight, because certainly what one doesn't want is for people to change your account number to theirs in flight, something like that. And optionally, client authentication. That means, is the client who I think it is? Today, when you hear the word authentication, you're going to think digital certificate. So what we're going to see in this protocol is certificates possibly flowing in two directions. That is the authentication. So how does this secure protocol actually work? That's what we'll talk about. And what do you do when you have problems? That is where our product, SSL Problem Finder, comes in. So in the beginning, there was SSL version 2, and of course SSL version 3. Those are quite old protocols. SSL version 2 is actually prohibited in RFC 6176, and RFC 7568 deprecates SSL version 3. When I say deprecate, that means that it is not recommended at all. So SSL version 3 should not be used. SSL came to the IETF and became the internet standard TLS, starting with TLS 1.0, 1.1, etc. 1.2 is the latest version. That is what most people in the field are using. There are some slight differences between SSL 3 and TLS, but minor. The biggest change is going to come about with TLS version 1.3, which is still underway at the IETF. And that's another whole topic which can take several hours in itself. So let's look at what happens with SSL or TLS. TLS, there is a handshake process. And this handshake process does what we talked about before. It does the server authentication, sets the stage for privacy and integrity. That means it figures out how are we going to encrypt the data. And what can happen is in between these packets, there can be problems. Anytime you have a flow, there can be error messages. One packet may not get there at the time that you really need it, and so there can be problems. And this is just one of the handshakes that is done for TLS. there are multiple. So let's start taking a look at some case studies. This is a relatively simple problem that SSL Problem Finder solved. What you do in order to use SSL Problem Finder is you take a packet trace. You take a trace of exactly what network packets went from one end to the other. You feed that in to the SSL Problem Finder packets, and then SSL Problem Finder analyzes what happens. He puts there's thousands of rules that it has inside Problem Finder about how the SSL protocols work. When I say SSL, you should be thinking SSL and TLS. I'm actually doing what most of the world does, which is to use SSL when I really mean TLS. So, as I say, SSL really means SSL or TLS, not really the SSL version 2 and 3 protocols. Those are no longer used. So we feed this trace into SSL Problem Finder, and it puts the rules against it, and there are a number of other things it does. It knows all the different kinds of handshakes there might be, what the packet flow should be, and what happens when there's errors. One of the hardest things is what happens when you don't get the packet that you want. And so after you've fed it in, you might get a screen like this. As I said, this is a very simple problem. And what the product found is that there were 2 handshakes in this particular trace, and both of them were bad. And what it found is that one of them had a certificate expired, and the other one was trying to create an SSL session on a port that was not defined for TLS. These are relatively simple problems that you can solve rather quickly. But it's an example. And so what I can show you, though, is the flow. And so what the product does, it goes through packet by packet and tells you exactly what is happening, that the client hello was sent, what kind of handshake it is, it's a full handshake, what packet is expected next, that is the server hello, when was that sent, what was the agreement on the cipher suite? And you can see in this case, it was TLS RSA with AES 128, etc., and so forth. And you can see down in the red that in this particular case, we did not get the next packet from the client, which is the client key exchange. We also received an SSL alert. And that SSL alert tells us that the certificate had expired. So as I say, this is quite a simple problem to get. We will be going on, of course, to quite interesting problems from here. So what expert systems really need to do is they need to figure out what it is that they don't see. So that becomes very tricky. It's a whole different level of analysis to say, I know what should be sent, and that's what I'm not seeing. You know, when you see things like hangs, when you see one side which just has the hourglass, it's waiting and waiting and waiting. Well, what is it waiting for? You have to know the protocol very, very well in order to know what is the next thing that should be sent. This happens, of course, in TCP as well as TLS. The other thing that expert systems need to do is take variables from one packet and match them with the other. You can see for the handshake process, there are multiple variables that we're taking from one end to match with the other. That's how we know how the handshake is proceeding. And then soon I'll show you about the data itself. We're going to need to match things within packets for data transfer as well. So let's take a case study, another case study. This is an analysis of good and bad handshakes with another kind of handshake, which is using a client certificate. This is more complicated. You can see that there are more packets that are sent back and forth, and between any one packet and the next, there can be problems. You know, what a lot of people say is just knowing these packets and what is sent after that, that in itself is hugely helpful for them, because it's very difficult unless you're doing these protocols all day long, as some of us in the IETF do, is to have memorized every single kind of handshakes and what can go wrong between every other. You know, really, that is something that computer systems should do. That's what software should do. Those rules are relatively straightforward. I say relatively, of course, because they sometimes depend on taking one field from one packet, matching it up with another 3 packets down. But it's relatively straightforward. What's not straightforward is adding the actual operational experience. And so that's the other thing that we've done too, is how does this kind of packet flow work in an actual live environment on very large networks. And we've worked with quite a few very large enterprises to put in quite a few of those rules. I have thousands of packet traces which have gone in to create SSL Problem Finder. So you can see here what we did in this case is we analyzed a good handshake so that we can see where things go wrong. And you know, that's something that's very good to do, is to see what is a good situation. And that way when things go wrong, you can say, okay, now I know what happened, is I have this good benchmark and I can match it up against something that did not work. And you can see from the packet flow how many different things happen in between the simple set of packets, how much agreement is done for these variables, and what is, you know, what is sent from either end. And you can see here that this is a packet flow with a client certificate. The red arrow is pointing to that. And you'll see the green at the top saying this handshake completed properly. Because not only are we looking for all the handshake protocol to complete, but if you look down at the very bottom, you'll see that data flow actually started. If we don't see data flow actually starting, then we're going to pause a minute and say, you know, it appeared to work. There may still be a problem. So next, you have a bad handshake. You can see here that it's much shorter. And of course, your biggest clue is that SSL Problem Finder highlights the portions in red. He says right away at the very beginning, this handshake did not complete properly. And you can see at the very bottom, the expert analysis saying that the client is not configured correctly, potentially, or the kind of certificate request that you wanted is not correct. You know, I've had people say to me, just this analysis in itself can save people hours of time in doing their work. And I joke around with people and I say, you know, we're not really interested in the easy problems. Where SSL Problem Finder can be the most use to you is when you have the tricky problems. It's those hard problems that only happen maybe, you know, a few times a week, a few times a month, that are going to take 80% of your time. We have people using the product every day, though. matching good handshakes, bad handshakes, to see exactly what's going on. We call them addicted to the problem finders. So let's talk about some other very difficult problems. Those are timing problems. And when we get to discussing our 300 handshakes in 1 hour, this is another area that we're going to talk about. So some of the hardest problems can be when there's a long delay in connecting or when you have performance problems in data transfer. Those can be very, very tricky. We've seen some really good connections add up to 200 milliseconds. We've seen some really bad TLS traffic double the response time or even more. So let's start taking a look at some of this. If we back up and think about what it takes to convert to TLS, if you're sending things in clear text, what do? Well, you start your connection, you do your SYN-SYNAC three-way handshake, and then you send some data. Well, that's easy enough. And so if you're using TLS, all you do is do two things in between. Of course, you start your connection, but then you have to do your TLS handshake. Do what I said before, figure out about server authentication, the encryption algorithm, and so forth, and then actually encrypt the data, and then you send it. So how hard could this be? That seems pretty simple. So what we're thinking is, how long does it take to start a connection, that three-way handshake? Oh, it should be microseconds, and now we may even be getting into nanoseconds. How much should it take to do a TLS handshake? Oh, at most 100 milliseconds, probably even less. And that's actually one of the very interesting things that's happening with TLS 1.3. How long should it take to encrypt the data? Okay, you've got to run the encryption algorithm over all that clear text. Still, that should be in the milliseconds. And then, of course, sending it should be milliseconds. Well, what if you have the nightmare scenario? Let's say your TCP handshake, it completes in microseconds. What happens if we take 10 minutes to do the SSL handshake? I know you're thinking, oh, for heaven's sake, that can't possibly be it. Well, I'm going to show you. Let's say in encrypting the data, we add 95% overhead. Oh, my goodness. And then in sending it, of course, because we've bulked up the data so much, that adds 95% of the time. You think, what a horrible thing, what a horrible set of scenarios. Let me just show you how you can make some very bad mistakes. Here's a 10-minute handshake time, and you can see from SSL Problem Finder, he's telling you it took 758 seconds to do that. And I have to say, when I first saw this, I was working with a very dear customer, and I couldn't even believe they had the patience to wait 10 minutes for the handshake to complete. And what had happened is they had misconfigured a subsidiary TLS protocol, which is OCSP, Online Certificate Status Protocol. Again, that's another thing we don't have time to talk about today. We could take a couple hours just talking about that. But how do you start looking at that? Well, of course, first you analyze the handshake, and you know what? In this case, the handshake completed correctly, but look at the timing analysis. You've got so much time, before starting the data transfer. You've got so many things in red. And what we're saying is we have a rule of thumb. Anytime we've got over 100 milliseconds between one step and the other, we're thinking that's probably a problem. And as the speed of networks increases, I know that time will go down too. And so here's another screen from Problem Finder, which is showing you 300 seconds, 78 seconds. oh, this is just awful. And you can see where is it? It's during the process of the handshake. Which end is it coming from? So you can see that there was a very, very serious problem here. There was a misconfiguration, a very simple thing to do. But without Problem Finder, it can take a very, very long time to figure out. And so what we really see the SSL Problem Finder and TCP Problem Finder products as is a partnership. What we want to do is we want to help out the network analyst. We want to help you be able to visualize the packets and the packet flow and point out to you very quickly where the problems might be. So once that part is done, then you can go on and very quickly try to resolve the problem. Now that in itself can take some time, but at least we've done a lot of work in helping you figure out where the problem is. You can see after they corrected the problem, the handshake time was in the milliseconds, maybe 200 milliseconds. Suppose some people could complain about that, but these people were very satisfied. 200 milliseconds rather than 10 minutes. That looks great. So let's talk about another terrible scenario, which is the 95% overhead. Oh my goodness, how did this happen? Well, this was with a file transfer. And how do you manage to do this? Well, they had written their own file transfer program. And, you know, I know some of you are going to say, well, that was the problem right there. So anyway, so how do you do this? Well, the application has to send data over to get encrypted. And if you send over a huge chunk of data to get encrypted, that's one thing. But if you encrypt it 1 byte at a time, that's a whole another thing. And that's what they were doing. Instead of sending big blocks, they were sending 1 byte at a time. And so then it was adding 20 bytes of overhead for every byte. And you can see that the original unencrypted file was about 2 meg, and once they encrypted it, it was close to 48 meg. And you can see in the application data records, there were 21 bytes in each application data records, of which 20 bytes were overhead. And you can see here, this is what the actual application data looked like. And you can see over and over again, when they're sending the application data, 21 bytes, 21 bytes, 21 bytes. As I say, it was 1 byte of data and 20 bytes of overhead. And SSL Problem Finder will look for things like that. He will say, are you sending packets with more than 10 application data records per packet? And what is your length? He's going to go through that kind of analysis. This is brutal. To do this by hand, manually, for a large file or something with thousands of packets, let alone millions of packets, that's just not something that one wants to do. As I say, let computer systems, let software do what it's best at, and the human being should concentrate on judgment. After Problem Finder tells you what the problem is, you can say, let me think what to do. I guess I'm going to have to walk over to the applications folks and start a conversation. So let's think about another kind of problem, which is the handshake time for the TLS handshake versus data transfer itself, or even the number of handshakes that are done. It's just like the TLS handshake is similar to the TCP, SYNX sequence or startup. The handshake time should be very small. I mean, when you think about it, the reason you have a connection is to actually send data. You know, you don't have it so that you can do a handshake. A handshake is just the initiation time. So let's just take a look at some. And this is a good connection. And so you can see that the handshake time, which is shown in yellow, is quite small. And you've got a large green bar, which is showing you the time of the data. And so this is good. Small handshake time and lots of data sent. Oh my, here's another one. And what are you seeing here? Oh my goodness, it just looks like it's all yellow. You see large amounts of time for handshake and maybe a very short, maybe 1 or 2 data packets sent, and then another handshake starts up. And sometimes not even any data packets are sent. And it may even be responsible for some very poor response time for you. Let's take a look at some more. Here, this is looking fairly good in terms of the handshake versus data proportion, but you're leaving sessions idle for long periods of time. And of course, that's up to you. A number of people, I know Google, Yahoo, most of the content providers, they will leave sessions open for long periods in case they need to be reused. And that's perfectly fine. It's just a question of how long and how many you want to have in that scenario. Here's some from Akamai, which is, of course, a CDN, a content delivery network, and they're left idle for long periods of time. And that's perfectly fine potentially. It just depends. It can add up. Oh my, here's another one. Again, sending very little data and leaving things idle for long periods of time. Here's one to Amazon AWS. Again, this is a way you can tune your network because the more ports that you have used, the longer your handshake time. That's all overhead that you don't need to be thinking about. Here's a long, long handshake, very little data. Why is this happening? And you can see inside, you can click into any of that with SSL Problem Finder, and you can see exactly where the long periods of time were. This happens to be between the server certificate and client response. And, you know, depending on where the problem is, between which packet and which packet, there can be a different reason. And SSL Problem Finder will tell you that as well. For example, you can see here that the large timing was time to validate the server certificate and the client key. So you know exactly what is the reason for this. Of course, now you've got to do your job and go ahead and try to figure out what the reason is. And so, of course, you can see too is how much time and relatively how many milliseconds are a problem. The screen that I showed you had to do with 41 milliseconds. And so 41 milliseconds is not necessarily a problem. The problem is the proportion of how little data is sent in proportion to the handshake time. I've seen people do many, many SSL handshakes unnecessarily when they could have left it open. You just need to analyze. And the problem is that without SSL Problem Finder, nobody really looks at these things. It's just too hard. But with SSL Problem Finder, it makes it quite easy. So let's take a look at one. This is the one that we were talking about in the beginning, where we analyzed over 300 connections in an hour. You can see now, after everything I've told you, that it's relatively simple with SSL Problem Finder to go ahead and analyze the connections. This was an interesting set of data. What this was is it was a trace taken with using Tor. Tor is the anonymous browser against the Great Firewall of China. So that's a very interesting set of traces. It was done by Princeton University, and we had access to that. But you can see here that 342 of those SSL handshakes were good and 43 were bad. So right away, we know what to concentrate on. We say, well, we may not care about the good handshakes unless there's a timing problem. We go over and say, the handshake time is possibly a little bad. One of them is almost second and a half, but the largest is about 8 seconds. So that may be something that we want to investigate. Again, we want to look at the next thing we want to do is we want to look at the TLS version. Because something that can happen is you can have downgrades. That is, you want to have TLS 1.2, but the server can't support it, and so he says, well, I'm going to do TLS 1.0, which is something you may not want in your network, and so we'll show you that. We'll also analyze if there's heartbeat requests. You may remember the heartbleed vulnerability that came out against a TLS. We'll look for that. And then, as we talked about before, we'll do an application data analysis to see if your encryption, how you're sending out your encryption, how the proportion of data to how you're doing it in terms of the number of bytes, if that is good or not. And then, of course, all the errors that we've found. And you can see sometimes that what we're seeing with things like we see a bad server cert, or we see a handshake complete but no application data traffic. This is a warning. You know, we may not want to see something like that. And then what the handshake alert. So you can quickly go and look at what was going on in each. You can also go through the timeline and you can see what is my proportion of handshake to data. This is looking pretty good. And then, of course, start looking at the handshake itself, as we did, and say, where exactly are we seeing the issues if things are slow? This is an interesting thing. A lot of the handshake packets will have something that's called the server name indicator, or SNI, and that's the server name. Oftentimes it's something like Google and Yahoo or Facebook, so on. But if you see something like this, which is this kind of random character string, that's the fingerprint of the Tor network. You can see that. That's the Tor browser and network have things like that. And so you can see that happening. So to summarize, this is a very tricky area. And as we move on to encrypt more and more, it's only going to get worse. And as we add TLS 1.3, there are even more complications. So soon we'll have to learn very well exactly what the protocol differences are between 1.2 and 1.3. And we are very involved ourselves in the TLS working group at the IETF. So we are quite familiar with the changes that are coming out. So thank you so much for your time, and let me turn it back for questions.
Thank you for taking the time to listen to our webcast. I hope you found something new or thought-provoking. If you have any questions or would like to talk to someone at SDS about SSL Problem Finder or any of the products in the IP Problem Finder product line, you can reach us at 1-800-443-6183, or you can send us an email, info@sdsusa.com. Thank you.